The long short-term memory network solved deep learning's hardest problem, holding on to a thought. By using a dedicated cell state and 3 separate gates, it learned exactly what to remember and what to discard across long gaps in sequential data. Looking at the deep learning tier of our algorithm grid, we find number 40, the Gated Recurrent Unit. Built as an evolutionary successor, the GRU keeps that powerful memory capability while shedding that heavy computational machinery. How exactly does a neural network match an LSTM using 25% fewer parameters? Achieving performance parity while stripping away structural complexity is the ultimate engineering win. To see how the GRU pulls this off, we must examine its predecessor's flaw. Looking at this unfolded sequence of a plain recurrent neural network, we see the baseline mechanism. The network blindly folds each new sequential input into a single ongoing hidden state.
For the network to actually learn from its mistakes, the error signal has to travel backward through every single one of those time steps during training. Over long distances, that backward traveling signal exponentially shrinks towards 0. The network physically loses the ability to update its earliest weights. Think of the sentence, "The cat, which had wandered the garden all afternoon, was tired." A plain RNN completely forgets the subject cat by the time it reaches the verb. Without a built-in mechanism to explicitly protect that signal from decaying, an RNN is structurally incapable of bridging long sequences. This diagram maps how the GRU solves that signal decay. Instead of an uncontrolled flow, it explicitly routes data through 2 mathematical checkpoints, an update gate and a reset gate, anchored to a single teal pathway. The reset gate calculates precisely how much of the past context should be kept and how much should be immediately discarded. Next, the candidate state generates a fresh proposed reality. It mixes the current input with the heavily filtered past provided by that reset gate. In this green schematic, we see the stark contrast to an LSTM. All of this complex routing happens on one single continuous line. The GRU completely eliminates the need for a separate dedicated cell state. Stripping away that extra state line removes an entire block of matrix multiplications per step. That cuts memory usage and accelerates training time significantly. This equation block shows the update gate, represented by the letter Z. It acts as the final arbiter, deciding the exact blend between the old memory and the new candidate state. If the network forces Z near 0, the math cancels out the new candidate completely. The old state is copied forward perfectly, completely untouched. Conversely, if Z approaches 1, the cell effectively drops the past and overwrites the hidden state with the fresh candidate data. Look at the sequence boxes from T1 through T4. The subject cat is locked safely behind closed gates at steps T2 and T3. It survives intact across the filler words, until the verb at step T4 forces an open gate and a new update. By giving the network the mathematical ability to hold a gradient perfectly still over time, the GRU beats the vanishing gradient problem, doing the heavy lifting of an LSTM without the heavy machinery. This comparison graphic outlines the primary architectural trade-off. The GRU sacrifices the highly granular, dedicated cell state of the LSTM to achieve a 25% reduction in total parameters. While the GRU trains faster and dominates on smaller datasets or edge devices, the heavier LSTM still holds an advantage when mapping datasets with extremely long-tail dependencies. Today, all of this highly complex recurrent gating math is completely extracted away by modern deep learning libraries. But how do we actually write this architecture into a single line of Python code? And how do we shape our data tensors so they flow smoothly through it? Understanding the underlying matrix operations gives you the power to choose the most efficient, precise tool for your data, rather than blindly deploying the heaviest algorithm available. When data flows through a sequence, because GRU complexity scales quadratically with the hidden state size, a developer who increases the units argument without understanding the underlying math can trigger a massive, unnecessary spike in memory and compute requirements. To master sequential models, we have to look beneath the API layer and dissect exactly what physical computing resources are triggered by a single line of code. This map tracks 50 essential computer science algorithms. We are using Chapter 10 of 50 Algorithms Every Programmer Should Know as our primary reference for this investigation, and we will pull the exact implementation from the book's open-source Jupyter Notebook repository. We are going to isolate the precise code block that instantiates the GRU and reverse engineer its hidden parameters. Here is the 4-line Keras sequential neural network snippet used to process the IMDb sentiment dataset. Line 1 initiates the model. This establishes a straight stack architecture. Data will flow strictly downwards from one layer to the next. The raw data, discrete integer word IDs representing movie review text, hits the embedding layer. This layer compresses a massive 50,000 word vocabulary into dense 32-dimensional continuous vectors. This 32-dimensional vector now represents the current input, mathematically denoted as x, for a single time step in our sequence. If we fed one-hot encoded text directly into the recurrent layer, the sheer sparsity of the data would overwhelm the system. The input data is now mathematically shaped and prepped, arriving at the threshold of the recurrent memory core. All of this leads to the critical third line, where the GRU algorithm is physically invoked. The integer passed to the units argument acts as the dimensionality anchor for the entire layer. Setting units to 64 dictates the exact size and shape of the hidden state, h, that will carry context across time. This single argument silently allocates the physical memory footprint of 3 internal weight matrices. The layer takes the 32-dimensional input vector x and the 64-dimensional previous hidden state h to perform its internal gating calculus. The developer simply typed units equals 64. They never once wired a sigmoid activation or a tangent function by hand. Understanding what lives inside this highway is what separates a framework user from an algorithm designer. This internal schematic reveals the nonlinear matrix math that the GRU executes inside that highway at every single time step. The first operation is the reset gate. Using 2 gates to blend a single hidden state is the precise architectural breakthrough of the GRU. This diagram shows how the isolated mass of a single time step unfolds to process a full sequence of data. The output hidden state of time step t becomes the input hidden state for time step t+1, carrying the accumulated context forward. Look at this sequence, but this design has a mechanical limitation. Because time step 3 absolutely requires the output of time step 2, the math cannot be computed out of order. This sequential dependency creates a robust information highway for context, but it makes the algorithm mathematically impossible to fully parallelize across time. This side-by-side comparison explains why Kyung-Yoon Cho and his team invented the GRU in 2014 to power neural machine translation without the heavy overhead of existing models. The older LSTM architecture requires 3 distinct gates, a hidden state and a separate cell state. The GRU collapses this into just 2 gates and a single state. Consequently, the GRU calculates only 3 matrix vector products per step versus the LSTM's 4. Time complexity scales as big O of h times h plus x per step. By reducing the memory footprint, GRUs train faster and fit easily onto edge-constrained hardware environments. When the sequential loop finishes and the sequence terminates, we reach the final line of the Keras pipeline. The final 64-dimensional hidden state emerging from the end of the GRU highway is caught by a dense layer. A sigmoid activation function squashes that context vector down into a single binary probability, predicting the sentiment of the text. Raw text was embedded, temporally processed through nonlinear gating mechanics, and distilled into a single decision, all driven by 4 declarative lines of code. The GRU is concise in code, computationally cheaper per step, and vastly more memory efficient than its older sibling. But a lighter algorithm only matters if it earns its keep against newer parallel architectures. Where does the GRU quietly lose out, and when must you abandon sequential loops entirely?
Where does a lightweight sequence model actually earn its keep in an enterprise deployment? In 2014, Kyung-Hyun Cho's team built the Gated Recurrent Unit, or GRU, to solve a massive problem in machine translation. They needed a more efficient way to power an encoder-decoder architecture, compressing a source sentence into a single dense mathematical vector, and decoding it into a new language. From there, the GRU rapidly expanded beyond translation. It became a go-to tool for speech recognition, text classification, and specifically time series forecasting. This unfolded recurrent network handles forecasting by processing streaming data step by step. It takes in one sequence element, like a daily stock price, at each distinct time step. Notice the horizontal path. It blends each new observation with the previous hidden state, carrying the historical trend forward. Any problem where data arrives over time and chronological order dictates the meaning of that data is the exact domain of the GRU. The primary design philosophy behind the GRU is algorithmic parsimony. It was built by deliberately stripping away the complex machinery of an older model, and despite the removed machinery, empirical testing showed the GRU consistently matches or beats the LSTM on many benchmark tasks, while converging on the right answers faster. The GRU proves that true algorithmic efficiency does not require compromising predictive power. You just eliminate the excess weight to solve the exact same problem faster. But that simplicity is a deliberate trade-off, and it creates strict boundary conditions for deployment. Referencing the right panel, the LSTM retains an edge on long dependencies and large datasets. Lacking that cell state, the GRU struggles with extremely long sequences. Ultimately, there is no universal winner. Engineers must empirically validate both models. There is also a strict ceiling for all recurrent models, including GRUs. They operate in the shadow of the transformer architecture. Because GRUs inherently process data sequentially, meaning they must wait for one time step to finish before starting the next, they cannot be fully parallelized. Transformers bypass this entirely, allowing them to handle massive, long-range language corpuses with far greater efficiency. The rule of thumb for modern deployments is this: reserve GRUs for fast, order-aware tasks on tight compute budgets, but abandon them for transformers when scaling up to massive natural language processing tasks. The evolution from LSTM to GRU offers a broader philosophical lesson for deep learning engineering. The GRU teaches us that the ultimate win isn't always adding more mathematical machinery. Often, it's shedding the excess and leaving memory alone. You can explore the Python implementation for the GRU in Chapter 10 of 50 Algorithms Every Programmer Should Know, with code available in the book's GitHub repository. But sequence models like RNNs, LSTMs, and GRUs blindly rely on receiving pre-packaged word vectors to understand human language. How does a machine mathematically embed meaning into those vectors in the first place? How does it inherently know that the concept of king is closely related to queen? That semantic mapping is the job of Algorithm 41, Word to Vec.